So I have uploaded as number of problems as possible with respect to your stiffness matrix method. So we have solved the stiffness matrix method for beam, continuous beam, non-sway frame, sway frame, and then we have solved for pin jointed structure also. If you don't find it convincing, or if you find that I should solve more number of problems on stiffness method, you send those problems so that I'll solve here and explain it to you. Okay. Anyhow, we'll go with the fourth module. I told you that after solving for the fifth module, we'll come back to the fourth module. So this is your fourth module. We need to analyze the structures using the matrix method of flexibility. Okay. So while explaining you the stiffness, I had explained you what is the flexibility also. I told you that flexibility is representing that if there is a displacement that is taking place because of the unit force is called as flexibility. Okay. So flexibility is the ratio of displacement divided by force. Okay. So displacement is equal to flexibility ratio multiplied by force matrix. Okay. So if I have to change this equation will become force matrix is equals to inverse of flexibility multiplied by displacement. Now you try to make a comparison between the stiffness matrix and the flexibility matrix. So what you used to determine in the stiffness matrix, you used to determine how much is the displacements, right? So here what we'll do is we'll calculate the displacements and we'll determine how much is the force. Okay. So if you remember in stiffness matrix, we used to find out how much is the displacements. Based on the displacement, we used to calculate the end moments, right, using the slope deflection equations. Here we don't need to do all of that, because after calculating, you are directly getting the end moments itself, or you will be getting the reactions. Okay. Now what I'll do is I'll directly solve a problem. I'll solve this problem, and while solving this problem, I'll be explaining you the method which you will follow to find out or to analyze the structure. Okay. So this is the continuous beam, which is having a two span of AB and BC, and it is loaded by a concentrated load of 100 kilonewton at the center, and for span BC it is loaded as a 60 kilonewton at the center itself. Okay. Now I told you that in case of your stiffness matrix, we used to calculate how much is your kinematic indeterminacy. Based on the kinematic indeterminacy, we used to determine how many number of coordinates to be applied. So on all those coordinates, we used to apply unit rotation or unit displacement. So in this case, what we will do is we will first define how many reactions are there. So here we need to define what is the static indeterminacy of the structure, right? So let us define what is the static indeterminacy of the structure. To solve the static indeterminacy, we need to first determine how many reactions are there. So let us go to first joint. At the first joint, it is fixed joint. So if it is fixed, there will be two reactions. Okay. So as there is no horizontal force, so there will be no horizontal reaction. So that's why it is getting eliminated. So there are only two reactions that will be generated at the A joint, which is MA, which is the moment reaction. The other one is vertical reaction. Okay. Similarly, at joint B, it is a roller support. Because of the roller support, it will be having only one reaction, which is RB. Now at C, it is again one vertical reaction, which is RC. So this becomes your free body diagram. So after knowing the free body diagram, we found out that there are four reactions. So 4 minus of 2 equilibrium equations will give you that 2 is your static indeterminacy. I hope you all remember how to calculate the static indeterminacy. You need to find out how many reactions are there, minus of equilibrium equations that will be used. So that will give you what is the static indeterminacy. So 2 is your static indeterminacy. Now what I'll do is this structure I'll try to release. So what is release? I'll explain. Releasing is to remove or to partially remove the number of reactions which are redundant in nature. Now let us understand what is redundant in nature. Redundant is that reaction, even if I remove that support, even if I remove that reaction, the structure will not collapse. Okay, the structure will remain stable. So that is called as redundant. So assume, like for example, if I remove RB and RC, this will become a cantilever structure. Now imagine I am removing these two support. Even if I remove this support, this structure will remain stable itself, because it's a cantilever structure. So cantilever structure is basically a stable structure, right? Now you try to imagine another way, like if I, for example, if I remove this RB and MA, so this will become simply supported beam, and it is a stable structure itself. Now this is how we try to release a structure. Now what I'll do is this is my method of releasing a structure. You can use any of the method. Either you can remove the reactions or you can remove the combination of reaction and moments also. Now here what I have devised to release this structure and to simplify the problem is that I'll take this structure and I release it such a way at RB joint I know that summation of moment will be equal to 0 because it is connected at this point. Now I'll convert this into pin joint. So if I convert this into pin joint, instead of continuous beam I'll make it as two different beams. So to do that, what I need to do is to apply the equal and opposite moments here. Okay, so let me call this as second coordinate. Okay, this part. Okay, as we know, this is another coordinate. This is MA. I'm releasing it. I'm removing these two. So this is my first coordinate. This is my second coordinate. Now these two are separate individual simply supported beams that are subjected to these two loadings after release structure. Now understand this, what I have done, I have taken this structure, I found out what is the free body diagram. From the free body diagram I am removing two of the reactions. What are the two reactions I am removing here? One is the moment reaction at the A end and the moments that will be equal and opposite at the joint B. By applying this moment here I am separating these two separate beams. Okay, it means what I am trying to create here a pinned structure. Okay, right. Now these two are different elements. Now what I will do is, in case of your stiffness matrix, what you used to do at the first and second coordinate, we used to apply the unit rotation. In this case, what we will do is we will apply the unit moment. Okay, so I hope you remember for span AB or span BC, we used to apply the at first coordinate and at second coordinate, we used to apply the unit rotation. So in this case, what we'll do is we'll apply the unit moment. What we'll do is at the first coordinate, let me apply the unit moment, and after that what we'll do is at the second coordinate we'll again apply the unit moment. So assume that if this is the structure, this is a simply supported beam. If I apply a unit moment at this point, if I have to determine what is the bending moment diagram, so the bending moment diagram will be like this. This will be 1 here and this will be 0 here, right? Now to calculate how much is the displacement, so for example, if I am applying a moment here, if I have to explain it like this, if this is some member, if I am applying a moment here, there is definitely a rotation that is taking place. So what is your flexibility values are? Flexibility values are calculating how much is the displacement because of the unit moment or force being applied. Now at the first coordinate I am applying the unit moment. So after applying the unit moment, I am trying to determine how much is the rotation that is created. So the rotation that is created at the first coordinate because of application of unit moment at the first coordinate is called as F11. Similarly, at this point also I will try to determine how much is the moment that is created because of the application of unit moment at the first coordinate. Okay, so to calculate that we will use this conjugate B method. So what is the conjugate B method? Basically, whatever the bending moment diagram is there, it will be loaded by M by EI diagram and it will be loaded on the beam. Okay, so if I calculate how much is the shear force at any given point, it will give me the rotation. If I have to calculate how much is the moment at any given point, it will give me the displacement, right? So this you know about the conjugate beam method. So what I'll do is I'll use the conjugate beam method in order to define how much are my values of flexibility. Okay, let us take this simply supported beam. I am taking this separately over here. So we know that the length is L. So here the length is 8 meter. So the M by EI diagram is 1 by EI diagram, which is triangular, maximum at the moment being applied and 0 at the other end. Okay, so this is your bending moment diagram. If I have to calculate how much is the reaction at this point, the reaction RA, I'm simply calling it as some RA or something. Okay, so if I have to calculate how much is the reaction here, what I have to do, RA into L minus of moment of this area. So how to calculate the moment of this area? First I have to calculate how much is the area of this. So area of this will be 1 by EI into a half multiplied by the length. So length is L. So what will be the area here? 1 by 2 into L divided by EI. Okay, so that will be the total area. Now the CG of this will lie somewhere here. Now with respect to CG, I have to find out how much is this distance. This distance will be 2/3 of L, and if I try to solve this, I will get to know how much is RA. Now RA is how much? L divided by 3EI. Now similarly, I can calculate for RB also, which is L divided by 6EI. Now I have solved this for some standard length of beam. Okay, using the conjugate beam method. If I apply unit rotation, unit moment at any given end. Okay, so at the near end where the moment is being applied, the reaction there will be L divided by 3EI, and at the far end it will be L divided by 6EI. So you try to remember it so that we can easily simplify the flexibility matrix. So this is the moment that I have applied here, and this is your near end, this is your far end, At the near end the reaction will be 8 divided by 3 EI, at the far end it will be 8 divided by 6 EI, which means what? This is the flexibility, or this is the displacement or the rotation that is taking place because of the unit moment that is being applied at the first coordinate, and this is the value of flexibility which is generated at the second coordinate because of application of unit moment at the first coordinate. Okay, so after solving these two, we can write down them over in the table. The next step is what? The next step is to go for second coordinate. At the second coordinate we will apply again the unit moment. So in both these elements the unit moment is generated, right? So here it will be 1 by EI and this triangle, and similarly 1 by EI in this triangle. Now if I have to calculate how much is the reactions that will be generated at these two ends, will be 8 divided by 3 EI, and at the far end it will be 8 divided by 6 EI. Similarly here also it is 8 divided by 3 EI, and here it is 8 divided by 6 EI, but it is not of any use by solving this because there is no third coordinate over here, right? So let us consider this one. What is this? This will represent F12. What is F12? This is the flexibility value, or you can call it as the displacement or the rotation that is created at this end because of application of unit moment at the second coordinate. So this is F12. And what is F22? F22 will be sum of these two, right? 8 divided by 3i plus of 8 divided by 3i. So let us substitute all the values in the flexibility matrix. So this completes our flexibility. Okay, now you try to solve the flexibility matrix for some more problems to understand this. Okay, in future also we will be solving more problems in which I am going to tell you how to solve these values. So let us solve the displacement matrix. To solve this displacement matrix, what we need to do is to find out how much is the M by AI diagram when it is loaded. So we'll take this release structure. So this release structure is nothing but your simply supported beams. So I'll take these two release structure over here and I'll load it by the external loads. So the external load over here is 100 kilonewton, here it is 60 kilonewton. So if I had to consider this as simply supported beam and calculate how much is the bending moment diagram, it will be WL divided by 4. So W is how much? 100. 100 into 8 divided by 4 will give you the value of bending moment in case of simply supported beam, and which is the maximum bending moment at the center. Okay. Now similarly we can calculate how much is the maximum bending moment in case of this element, which is BC element. So again it will be 60 into 8 divided by 4, which will give you 120 by EI. So this is your M by EI diagram. Now once you calculate how much is the M by EI diagram for both the elements, next thing is to calculate how much is the reaction over here. So if I have to calculate the reaction at this point, I'll do in a more simple way. First I'll take the total area of this triangle and I'll divide by 2. So 1 by 2 into 200 by EI into 8. This should be divided by 2 because it's a symmetrical bending moment diagram. So the reaction over this side and this side will be half of that. Okay, so the value of that will be, so here it is 400 by EI. Now similarly we can also calculate how much is the reaction for this. So the reaction for this will be here it will be 240 by EI. So we know that these are our reactions. These reactions are nothing but our displacements. So the displacement matrix would be like this: 400, 600, 1 by EI. Okay, so once we have solved the displacement matrix, once we have solved the flexibility matrix, the next step would be to solve for force matrix. So force matrix will be equals to, okay, so the one change that I have to do here is to apply negative to this displacement. So we need to apply negative of displacement matrix. So we need to apply negative to it. So substitute these values over in this equation and find out how much is force matrix. So the force matrix that I have got is this much, minus 102.25. The other value is 94.285. Okay. So these are the values of our forces, and what are the forces that we have calculated? These forces are nothing but your MAB and MBC values. Okay, so MBC is equals to minus of MBA, okay, which we already know. Okay, so this is how we determine how much is the end moment in case of flexibility matrix. Okay, so you try to understand this problem. If you find difficulty, anyhow we are going to solve more problem on this method.